All right, welcome back everybody to the seminar. So our next speaker is Sarah Tymochko from UCLA, and she'll be telling us about time series analysis with zigzag persistence. So Sarah?
Awesome. Thank you so much for the introduction, and thank you to the organizers for inviting me. I'm sorry I can't be there in person. It's the first week of teaching here. Quarter system is weird, but I'm glad I can be here virtually and see a bunch of the talks so far. Right, so today I'm going to be talking about, as Liz said, time series analysis using zigzag persistent homology. So we are all TDA people or computational people, so we know that there's some notion that data has shape. When it comes to looking at images, this is particularly obvious, but time series also have some sort of notion of underlying shape. And we can often detect this shape by embedding it into a higher dimensional space. So in this case, something like a periodic time series here with a bit of noise ends up looking like a collection of points in this sort of circle or annulus shape. So TDA is really great for detecting circular features. And so being able to pick up these underlying patterns in time series data is a really good pairing of the two problems. So that embedding that I mentioned is something called the time delay embedding. If you've seen this, bear with me, but the idea is that if we have a time series, which I'll just think of as a sequence of points, we can embed this into some d-dimensional space by choosing some lag parameter tau. And so we end up with a collection of d tuples in Rd, and each one of those points are spaced tau apart in the original time series. So when we're embedding into something like R2, this looks like taking 2 points, maybe this blue one and this red one here, and then pairing those up to be a point in R2. So here, taking the red coordinate, we get the x-axis here, or the x-coordinate, and the blue value gives us the y-coordinate. So if we do this for each step along the time series, sort of sliding these 2 points along, we trace out this circular feature. So if we've chosen things correctly, then periodic time series end up looking like circular features. And so this tool is a really powerful tool in dynamical systems. And to prove that to you, I'll just show a quick example. So the Lorenz system is this fairly famous chaotic butterfly pattern. And if we know the full system, we can plot all 3 coordinates at once. So we can solve this for some set of initial conditions and follow the trajectory over time. So we know what that really looks like based on this system, but let's say we didn't, and for some reason we were only able to record one of the coordinates from our system. So rather than being able to keep track of the x, y, and z, now all we know is how that x value is changing over time. So we've lost 2/3 of the information here. If we try and go backwards and embed back into a higher dimensional space, choosing a 3-dimensional space, we can end up with a reconstruction that looks like this. And so while it doesn't look identical to the original system, it still has the same topological features that we're interested in. We can still see this sort of butterfly shape, just if the wings are a little stretched out. And so by using this time delay embedding, we're able to still capture these tools, but using a lot less information. And this is really important when it comes from a data-driven perspective, because we often don't have full knowledge of what we're studying when we're looking at how things evolve over time. So there's lots of different shapes that can appear in these time delay embeddings. If you have a periodic time series, again, this is assuming you've chosen things correctly, which I'll be a little vague on, but you end up with a circular feature for periodic time series. We see this one's a little bit wobbly, but topologically still a circle. On the other hand, if we have something like a quasi-periodic time series, then we can end up with a torus shape. And TDA is a really great tool to be able to distinguish these types of features. So there's been a long history of persistent homology being used for time series analysis, particularly with this time delay embedding. This is a very incomplete summary, but a lot of the initial justification for why this is a legitimate combination of tools was done by Jose Perea. and then extended to the quasi-periodic time series case as well. And then there's been some work using witness complexes to study these, and a whole slew of applications, from biological applications to engineering to finance to everything under the sun. So there's been a lot of work in this direction, where most of these look at some sort of combination of taking a time series, embedding it with the time delay embedding, and then computing persistent homology on that collection of points. And that's great. Also, the same caveat as Liz's presentation, I'm sure I left out papers here. And if I left out yours or your favorite application, please let me know. As I said, this is a very incomplete list, but just wanted to touch on the fact that it applies to so many different cases. The problem that I want to talk about is, what if you have multiple time series that's coming from the same sort of system or the same application? So here we could imagine each one of these time series comes from the same experiment, but where we've changed some parameter value a little bit. So here, this is just a synthetic example with noisy cosine waves or noisy sine waves, I guess. But all we've done here is something that increases the amplitude and then shrinks the amplitude back down. So we could look at the time delay embedding of each one of these time series and see that, as we can expect, we get a circular feature that gets larger with the amplitude and then shrinks back down. But by computing persistent homology on each one of these individually, we might not capture the fact that this is, or we wouldn't be able to relate the fact that this is all coming from the same system. These are just 9, if I can count, different collections of point clouds. And we want to capture the fact that there is some underlying connection between them. So the tool that we'll use is Zigzag persistent homology. So rather than our standard setting where we have to have inclusions all going in one direction, we can have a filtration where we end up with inclusions going in different directions. So we could have one simplicial complex that includes into the next, but then the second one includes back into the first one. So we can end up with this zigzag pattern or any pattern you want, and all of the math still works out nicely. These induce maps on the homology groups, and we end up with a zigzag persistent module. And so we can still capture sort of this changing topological structure, but through the zigzag rather than a sort of standard filtration. And so this setting comes in really nicely because we don't necessarily have that with all of our point clouds. We have some nice set of inclusions, so we can sort of arrange things the way we want to pick up patterns throughout. So let's start with a simple example just to see how this zigzag persistence works in this setting, or how we're setting it up. So if we just have these 5 point clouds that look like circles, just of arbitrary radius, we may want to capture sort of which features are similar in moving through that collection of point clouds. So the blue and purple circles are fairly small, but it does kind of look like going from orange to green to red. You just sort of have this shrinking effect. So can we pick up sort of the different circular features in this collection of points? And so the way that we'll do this is set up a zigzag by just taking the union of the point clouds in between. So this gives us something that looks like this with that example, where we just now put the blue and orange points on top of each other, the orange and green, and so on. But of course here, there still isn't really any interesting topological structure. All we have is individual points. So while we can visually see that these are different circular features, and here sort of the orange and green features are similar, and the green and red features are similar, we're not able to pick up that using anything, since these are all just discrete points. So what we'll do is connect the points using the RIPS complex. So we can pick some radius, or even a collection of radii, and just arrange things so that the inclusions work out. And if we do that, we end up with these simplicial complexes where we can actually compute things nicely. So we can visually see that we have some sort of circular feature on this end that gets filled in when it's included into the orange circle. But then we have this middle range of values where we have a circular feature that persists through that range of the zigzag. So if we were to compute the zigzag persistence of this, we can sort of visually, as I mentioned, see that this is the circular feature that we'd be likely to detect. And this appears in the zigzag persistence diagram as a point that is born at 1, meaning the first point cloud here, if we start counting from 0, and it dies at 3.5. So this indicates that it dies between the third and fourth point cloud in that union in between. And so here we're able to see, based on these points in our zigzag persistence diagram, what sort of features we're seeing in our original data. So very simple test case, but here our birth and death are corresponding to the index of this, counting these point clouds rather than some sort of scale feature. So it's a different interpretation than standard persistence diagram. So going back to our time series example, we can see that the sort of collection of random circles matches nicely with this time delay embedding of each of these noisy sine waves. So if we, the goal here would be to detect where you're sort of seeing changes in the time series where maybe the noise is overpowering the signal or vice versa. So here we can see on either end that our time delay embedding, we're not seeing that circular shape because the noise is sort of removing any of that information. But once you start getting to the higher amplitude values, the signal is stronger than the noise, and we can see those circular features appearing. So if we set up the zigzag, this is a little bit hard to read, but if we want to read across the rows, so we have the original point clouds where we've computed the RIPS complex, and then in the middle, we're taking the unions. So here we can see that around the first point cloud x1, we can see a circular feature appear that persists if we move through all the way up until around the union of 7 and 8. And so if we look at that in our zigzag persistence diagram, this point that's born at 1, so it starts at the orange point cloud and it dies at 7.5, indicating it dies between the gray and the final point cloud, green. And so this exactly picks up the range where we are seeing some sort of signal appearing rather than the noise. So it's detecting what we expected it to detect. Oops. And so the real sort of underlying motivation for this project was to look at bifurcation detection in a data-driven manner. So dynamical systems undergo these changes depending on a choice of parameters. And in theory, there's lots of ways to explore this, but in practice, this can just look like a drastic change in your time series behavior. So being able to detect when that change occurs or when it flips back can be an important thing to study. And so this is entirely from a data-driven perspective where the literature of tools from the dynamical systems community isn't particularly useful. So one example here is this Selkov model for glycolysis. It's a two-dimensional system with the equations given here. And the goal, we can see that if we solve this for different, pick an initial condition, let it go for some time, and then cut off the beginning, we can see the different system behavior by just changing this different parameter value b. So for small values of b and larger values of b, you end up with solutions that are fairly stable. They end up going to the same point, but in the middle, you end up with these limit cycles. So you end up with this circular behavior where you're tracing out these features. And so this, in this particular system, is a Hopf bifurcation, if that means anything to you. But really, the sort of data-driven perspective is if we see this drastic change occurring, where we go from some sort of consistent behavior to this limit cycle behavior. And so the way that these point clouds here are generated is to pick one value of the first parameter A and then vary the B parameter. But as I mentioned with the Lorenz system, in an experimental setting, we often don't have full knowledge of the system. Here we have both the X and Y, both the equations for the X and Y coordinates. And so just like the Lorenz system, we're going to drop this down to a more realistic setting by just keeping track of the X coordinate time series. And so this can mimic an experimental setting where maybe if you're not a mathematician like me and you actually sit in a lab somewhere and turn some dial that chooses some parameter for your system, you could end up with a different time series depending on what parameter you choose. So now we have this setting that we've set up everything for in this zigzag persistence, where we have a collection of time series with some sort of changing parameter value, and we can visually see this drastically changing behavior. So can we detect that using zigzag persistence? So the first step, it seems silly, but again, this is trying to mimic real life as close as possible. But so we reduced it down to a one-dimensional system, and now we want to reconstruct the features using the time delay embedding. And so we can see it doesn't look exactly like if we used both the X and Y coordinates from the system, but we end up with the same topological features that we saw before. So now we've built back up to 2D using this time delay embedding. And if we compute the zigzag of RIPS complexes, we get something that looks like this. One note is the point clouds may look a little bit more sparse here. We did use landmark complexes because, especially with these, well, in either case, if you're staying put at one point, you don't need all of those points to know that. And if you're tracing out a limit cycle, you don't need a million loops around that cycle to determine that. So we downsampled our point clouds using landmark complexes and then computed these RIPS complexes. And here we can see that we're picking up sort of what we would pick up visually with our eyes, where we see a circular feature appearing around X2. Moving through, that circular feature still persists, and up until this middle between, this union in between X8 and X9. And so in our zigzag persistence diagram, we get a one-dimensional feature that's born at 2 and dies at 8.5. And so again, this is just counting the index of the point cloud for simplicity, but we can map this back to our original system and see that this is telling us we have some sort of drastic change occurring between 0.4 and 0.5 that persists until between 0.75 and 0.8. So visually, this is what we would expect the zigzag persistence to detect. And it's actually known that for this particular system and these particular parameter choices, that there's a Hopf bifurcation from about 0.4 to about 0.8. So we are picking up almost exactly that range. And if we did a more fine-grained discretization of the B values, we probably would get even closer. So while we may not always have the ground truth of where this bifurcation occurs, this method allows us to get a good approximation when compared to the original system. This tool could also be particularly useful in something like time series where the behavior varies over time. So here we have this time series that we can see as periodic, but the amplitude changes quite a bit throughout. And if we were to compute the time delay embedding of this time series, we would miss the fact that there's any periodic behavior, because you would end up with these sort of circles of various sizes where topologically we wouldn't see any one-dimensional features. So the sort of standard pipeline for analyzing this time series using TDA would not be particularly useful. So instead, what we can do is break it down into a more localized time series. So pick different windows. Here we've just divided the time series up into 7 windows. You could do something with overlap if you wanted. And if we compute the time delay embeddings of these, we can see that we pick up those circular features a lot more clearly. So you still don't see it all the time, where on either end, you sort of have these filled in points, but at least in this middle region, we're picking up that there's some drastic change occurring. So once again, if we compute our zigzag persistence diagram, we get a point that's born at 2 and dies at 4.5. So we have something that's born here and dies going between this one and this one. So it would indicate to us where exactly you're seeing the most drastic change. And again, if we sort of did smaller windows or some sort of overlap, maybe we would get a better detection. So we call this method the bifurcations using zigzag method, or the buzz method, because acronyms and why not. But the idea is starting with some sort of collection of time series where you have some sort of relationship between them or some sort of ordering on them that matters to you. You can compute the time delay embeddings of each, convert them to the RIPS complexes, and then compute the zigzag persistence. And so this allows us to relate not just looking at the topology of one single point cloud, but relate this collection of things. And then we can map it back to our original system to be able to understand when these drastic changes are occurring in the original data. So a very data-driven approach, but it allows us to connect between sort of some underlying system and what we're seeing from the topology perspective. Oops. And so as with any method, there are always pros and cons, and I like to be transparent about both. So one benefit of this is that it bypasses the computation of numerous persistence diagrams. So while we could compute a persistence diagram for each one of the input point clouds, that can be computationally difficult, and it also runs into the problem of what do you do after the fact. So there are lots of methods that vary from maximum persistence to machine learning, but that requires some sort of choice. And so in this case, we are able to summarize all the information in one persistence diagram or zigzag persistence diagram. And so we don't have to choose sort of a post-processing after the fact. And of course, we've shown that this example works, or this method works on a variety of synthetic examples. The cons, of course, computation is going to be the biggest one here. So longer time series give you more points in the time delay embedding, which computationally makes things less fun to work with. RIPS complexes are expensive to compute. And then the one thing I sort of swept under the rug or skipped past is what radius do you choose for these RIPS complexes. So we did some testing of how robust it is to your choice of radius. And of course, that's going to depend a lot on your original data. But there is some hand tuning that's required to get these to give you meaningful results. And so there are future directions of this work, I think, which may be presented tomorrow by David, that look at a sort of network version of this. So keep that in mind for tomorrow's talks. But yeah, so the balance here is computation with convenience in some ways. And so, yeah, this is joint work with Dr. Liz Munch and Dr. Frascasone from when I was at Michigan State. Thank you all so much for listening, and I'm happy to take any questions.
Thanks, Sarah. Are there questions? Yep.
Hey, Sarah, thanks for the presentation. I was wondering about the computation itself. So what do you actually use for there's a zigzag specific computation you have, or?
Yes. So for zigzag persistence, we are using, I believe it was Dionysus, but at some point we might have switched to Goody. I can't remember. They both have it, I believe. I have heard that there's newer zigzag code that is faster, but the zigzag persistence itself is also a bottleneck in computation.
And then, sorry, a follow-up question. So in general, if you could go back one slide, so so like in this example, the only thing that's changing are the number of edges, right? Is the number of vertices fixed? I know that that's not true in the general case.
The number of vertices doesn't necessarily have to be fixed.
Right. I guess in your applications, you usually have like a fixed point cloud that changes in the zigzag behavior, such that the only thing that is changing is on the relations.
So the problem with the time delay embedding is we don't necessarily, we know that these point clouds are related, but we can't really map like one point to the next, because you could choose different values of tau, for example, in the different embeddings. So then it's hard to say that like this particular point from this particular time series matches with this point in this time series, because they could end up on sort of different sides of the circle, and it just gets you can't really keep track of that in a nice way that makes sense. So here we treat each point cloud as completely separate entities without any relationship between them, which is why taking the union gives us that sort of connection.
I see.
Can I? So just to follow up as an advertisement also, we have a very fast zigzag code available, and it's a work, probably you don't know, please try it. People have tried it and it beats the others.
Awesome. Yes, that's been on my list
Fast
of.
zigzag.
Is it, well, is it posted on, where is it, GitHub or is it?
Yeah, it's
Okay,
on
cool.
GitHub of Taos.
That's been on my list for someday improving this code, and I know that one exists. So
Howard?
Yeah, so when you say that Roots complexes are expensive to compute, you compute the whole complex and then afterwards you look at the radius, or can you somehow bypass a lot of the computation if we know the right radius you want to use?
yeah, so we don't compute the full RIPS filtration. We just pick some radius to start and and then compute the RIPS complex. So just computing sort of one step in the RIPS filtration is also computationally expensive, but definitely less bad than doing a full RIPS filtration on each one.
Hi, thank you for the talk. So maybe I'll ask, but so you're always computing the RIPS filtration on a two-dimensional object, point cloud, or the higher dimension? Because if you're just interested in something that is, so if your points are always in a 2D ambient, then I will go by alpha filtration, not RIPS filtration. That will speed up a lot.
Yeah, that's a good point. I guess for all of the examples we've looked at, it's always been embedding into 2 dimensions, but it's quite possible that if you applied this to real data, that it wouldn't, embedding it into 2 dimensions wouldn't necessarily be the right dimension to look at. So there are the choices of the dimension and the tau for the time delay embedding. And we sort of wanted to leave this method to be to work regardless of those choices. So in theory, you could end up with something in higher dimensions, but that's a good point that for 2 dimensions, it could be optimized better.
In the general setting, it's just if you want to speed up an application and you know that you are 2D, then
Yeah. That's a good point. Thank you.
Can you expand on the, like, how do you choose the radius for the RIPS complex? Because it may happen that the circle gets larger and none of your Euclidean balls intersect. And then you'll get like, not a circle, you'll just get like a bunch of points.
Absolutely, yeah. So all of these examples were sort of hand-tuned in that we could look at the collection of point clouds and see what sort of this maximum distance was that we would want to match with, or we would want to fill in, while also keeping the smaller features visible. So for the first example I showed with just the 5 random circles, that one, a different radius was picked for each one of the circles for convenience of the example. But in the last 2, using the, I guess all of these ones, including this part, were just picked using one small value. So you can look at sort of the range of values of the points and get a good approximation by eye. Coming up with some sort of heuristic was always on my wish list for this project, but that sort of moves us back in the world of persistent homology, because that's sort of the nice thing is we don't have to pick a radius. So I think there's future or other versions of this work, in particular by Auden Myers and David Munoz, who I think is there, that have an approach that doesn't require you to choose this radius. So I think that's a better direction than trying to optimize things on this end.
You know, you can just find the maximum distance of pairwise points of all the complexes here.
Yeah, but you don't want the maximum distance between all of the points because you don't want to fill in the circles. And so I'm sure there could be some way of coming up with a nice heuristic here, but maybe is application dependent, or for sure is application dependent.
Thank you.
All right, so for the sake of time, I think we'll do more questions offline, but let's thank Sarah again.
Thank you.